Hello, everybody. Welcome to this new AIDRC seminar. So today it's our pleasure to welcome Dr. Amin Sadeghi, who is a senior scientist in Qatar Computer Research Institute. So Dr. Amin has a broad experience in machine learning, in particular computer vision and natural language processing, and also in creating AI startups. So today he's going to talk about WhiteGrad, which is a new fast neural network optimizer. So Dr. Amin, the floor is yours.
Thank you so much. Thank you so much. Can I just use this microphone? Okay, thank you so much, Mastan. It's a great pleasure to be with you guys. So just a little bit about my background. I am a senior scientist at Qatar Computing Research Institute. I was invited to attend MIT a few years ago, but unfortunately I was unable to get the visa. Before QCRI, I was a faculty member at the University of Tehran in Iran. And I also have work experience at Amazon and Google and Adobe. I was graduated from University of Illinois, Urbana-Champaign. And other than this, I have had a number of startups in AI. And I have exited from 2 of them. So let me start with explaining the basics of this optimizer. So in machine learning, in deep learning, you usually have a loop like this in your training process. And this loop has a number of steps. The key steps that we want to look into is this backward step when you run backpropagation and the optimizer step. An optimizer updates the model parameters. So let me start with this simple example. Imagine we have a simple image classifier that accepts images of either digit 1 or digit 0. And let's say we also have a layer at the end of the model where the input is 3-dimensional and the output is 2-dimensional. So the output tells you either it is 0 or 1, so it gives a score for 0 and a score for 1, and the input is 3-dimensional. So you have 6 parameters here in this layer, right? 3 of them promote 1 and 3 of them promote 0. So when you see 0, whether the output of the model is 0 or whether the output of the model is 1, all the parameters that promote 0 will be amplified, right? And all of the parameters that promote 1 will be reduced, right? Basically, because this is 0, anybody that helps increasing the score of 0 will increase. And any parameter that tries to increase the score for 1 will decrease, right? Because the answer is 0. If you output 0, your loss will be small or 0. Or if you output 1, the loss will be high. So basically, it turns out that every parameter that promotes 0 will be increased, and every parameter that promotes 1 will decrease. But if we see a digit of 1, it's completely the other way around. So all of the parameters that promote 1 will increase, and all of the parameters that will promote 0 will decrease, right? So that's very simple, right? Because I think it should be clear that these parameters always promote 0, right? Because the activations here are positive if you have ReLU. So this is going to be the dot product of a positive vector and a bunch of parameters. So if these parameters are high, then the output will be high. So if you think about it, in the training process, anytime that we see an input of 1, all of these parameters that promote 1 will increase, and all of the parameters that promote 0 will decrease. And whenever we see a 0, all of the parameters that promote 1 will decrease, and all of the parameters that will promote 0 will increase. And this is really a very practical example. And what happens in practice is all of these parameters have a lot of correlations, right? So if you say, for example, if you take G1 and G2, any time that G1, the gradient of G1 is positive, the gradient of G2 will also be positive, right? And the other way around. So there is going to be, so even though these parameters have 6 degrees of freedom, even though you have 6 parameters, but they are very highly correlated in practice. And this correlation is not good, because imagine you are here, your parameters are here. This is a 2-dimensional example, but you can imagine higher dimensionality. This is going to be valid for high dimensions too. So if you're here and your target, the optimal configuration of parameters is here, then what will happen is you will only be allowed to take these steps, right? Because all of the steps that you can potentially take are highly correlated. So you can allow steps like this. So your optimum path to the target is going to be a very bad zigzag path, right? So it means that optimization will be very inefficient, just exactly because the gradient of these parameters are highly correlated. But if the gradients were not correlated, your path would have been something like this, right? You were able to get gradients that can directly go to the target. So this is why having correlation in the gradients is not helpful in training. So you can think of the covariance of the gradients. If you have a 6-dimensional gradient vector, the covariance of the 6-dimensional gradient vector is a matrix that is 6-dimensional by 6-dimensional, right? If you think about the covariance matrix, if the gradients are completely decorrelated, and if they have the same distribution, your covariance will be identical, right? So like each gradient could have one random direction, which with respect to any other gradient, and the covariance becomes identical. If all of the parameters are decorrelated, then the covariance becomes diagonal, right? So there is no covariance between any, for example, sigma 1 and any sigma 2, right? So the covariance becomes diagonal, but then the variance of individual parameters could be different. But then what happens in practice is not only the gradients are not IID, but also they are non-diagonal either. I mean, they're not diagonal either, right? So any parameter has covariance with any other parameter, right? So this is a bad situation for training, right? Because like every pair of parameters are correlated. So if you think about what happens in standard stochastic gradient descent, so at step T, you can calculate the gradient of the weights at step T. And then we call this MT. And then we have a learning rate, which we call eta. And then the way we update the W's, the weights, is we multiply our learning rate to this gradient vector. MT is the gradient. And we basically subtract this from W. And then this is how we update W, right? So this is the standard stochastic gradient descent process. The idea of momentum is instead of using the gradients as the update vector, we just run a exponential moving average. We get the exponential moving average of the gradients, and basically we use that to update the model. And the way it works is we have some factor named beta, which could be 0.9, right? Something like 90%. So we get 90% of the previous M plus 10% of the current gradient. So basically, this idea is similar to momentum, because like the gradient of this is like the update vector of this step has a lot that's shared with the previous step, right? And then the way momentum helps is it will try to make this zigzag pattern a little bit less serious, right? So it will soften the and of course momentum is helpful in training. It will help you speed up training exactly because it will turn the gradients from this zigzag pattern to a slightly better pattern. And then the idea of Adam optimizer is also very similar. I mean, it has a number of new tricks and ideas in it. So MT is similar to how momentum works, is the momentum of the gradient. But then we also introduce VT, where VT is the momentum of the gradient squared, which they call the second moment of the gradient, right? It's the same. Basically, instead of taking the moment of the momentum of the gradient, we take the momentum of the second power of the gradient. So basically, each element or each dimension of the gradient is raised to the power of 2, right? So this is called the second moment. And then when we want to apply the update, instead of, I mean, of course, we use MT, which is similar to the gradient, which is similar to the momentum. But then we also add a term, or a factor of 1 over the square root of VT. So it means for each parameter, if the previous variation or the variance of the gradients updates has been high, then dampen this gradient, right? And if it is low, then amplify. So basically, imagine, let's take just a single parameter. For a single parameter, if the variation of the update for that parameter is high, so basically in one step we get a very high positive update, and in one step we get a very high negative update, right? In that case, VT becomes large, and we multiply the update by 1 over the square root of V, right? Which means we dampen this. Basically, Adam has a technique to get rid of the variance of the updates, right? So if one parameter has a very high variance of the update, and another parameter has a very low variance in the update, then it will try to dampen the update of the high variance parameter, and it will try to amplify the gradient of the low variance parameter, right? So this way, Adam speeds up the training process, right? I mean, it should be clear, right? The idea should be clear, right? So basically, the idea is, see, like what happens in practice is some parameters will have very high variance, some parameters will have very low variance, and then you will still have this zigzag effect. And this zigzag effect is basically due to the fact that in some directions, the variance or the updates have a high variance. So sometimes the update says increase the parameter, sometimes the update says decrease the parameter. But whenever it says increase the parameter, it says increase by a lot. And whenever it says decrease the parameter, it says decrease the parameter by a lot. Right. So basically, Adam optimizer controls the variance of the updates and it speeds up the training. So basically, if your updates are like this, and you have a high variance along some dimensions, for example, here in the vertical direction, there is a high variance. But in the horizontal direction, there is a low variance. In this case, the covariance matrix is diagonal because the parameters are decorrelated. And basically, Adam is able to turn this into like a identity covariance, and this way it can speed up the training process. Right. But then, because the adjustment is done element-wise, the adjustment is done element-wise in Adam. If you have correlation in the gradients, right, you cannot get rid of the correlation in the gradients, right? Because when you do element-wise adjustment, you assume that the gradient or the covariance is diagonal, right? So like, for example, you can imagine, like I can just give you a very practical case. For example, in this situation, right? Let's say you are allowed to amplify each dimension and dampen each other dimension, right? Can you get rid of this correlation? Right? There's no way, right? By amplifying one direction and dampening another direction, there is no way to get rid of this high correlation. But if the correlation, if there was no correlation between the gradients, then you could have very easily gotten rid of the high variation, right? So this is basically the failure point of Adam. And Adam is the like most widely used optimizer, and it's like the most highly cited paper in the 21st century. And still it has this flaw, where if your gradients are highly correlated, it cannot get rid of the correlation, and as a result, the learning will be slow. But then, yeah, we discussed it would have been nice if the gradients were decorrelated. Some of you may have heard of higher order optimizers, right? Like, for example, Newton's method is a higher order optimizer. BFGS and LBFGS are higher order optimizers. Conjugate gradient method is a higher order optimizer. The idea behind higher order optimizer is not only when you're here, not only you look at the gradients, right? So if you're here, if the parameters are here, the gradient is going to be high, but you also look at the curvature. And the curvature helps you figure out how far you should go, which direction you should go. And these higher dimensional, these higher order optimizers, actually they do much better in the sense that they need much fewer steps to converge, right? So they learn much faster. But let me ask you guys a question. If higher order optimizers are so good, how do you, why don't people use higher order optimizers? Right? Why higher order optimizers? What? Exactly, because of the computation cost, right? So if you want to use higher order optimizers, like second order optimizers, you need to calculate the Hessian of the updates. And if you have n parameters, the Hessian matrix itself is n squared, has n squared parameters. So like if you have a million weights, we were just talking about this large language model that some of you guys trained, which has 60 billion parameters, right? So even if you have a million parameters, then the covariance matrix will have 1 trillion parameters, right? So it's completely interactable in practice, right? So and not only, so this is just the memory requirement, and the computation requirement is even worse, right? So basically it's completely interactive. So, even though second order optimizers are cool and they're fast, they need fewer steps to train, but they're not practical for deep learning, right? Exactly because they're computationally expensive. And you guys, some of you guys might know, first order optimizers use gradient, second order optimizers use gradient and curvature. First order optimizer, each of their steps is faster and requires less computation, and higher order optimizers are slower. Basically, each step requires to get some knowledge of the covariance, so it's slower. And then first order optimizers have less progress every step, and higher order optimizers have more progress every step. But then the question is there a way that we can make use of second order optimizers in deep learning? It would have been very nice if we could have used second order optimizers in deep learning, because the training would have been faster, right? But it is not possible because calculating the covariance is tricky. So you can think about these training techniques as a spectrum of first order optimizers and second order optimizers. A stochastic gradient descent is a first order optimizer. It doesn't take care of, it doesn't pay any attention to curvature. Adam pays a little bit of attention to the curvature, because if you think about it, when you calculate the variance of each individual parameter, it gives you an estimate of the curvature, right? If the variance is high, it means that the curvature is high. And if the variance is low, the curvature is low. But it only uses this curvature information only for only along each individual parameter. Right? So every parameter is completely independent of every other parameter. Then on the right side, there is Newton's method that literally explicitly calculates the Hessian matrix, which is very costly to calculate. And then, but there are also some other techniques that are second order, but they don't need that. For example, conjugate gradient method doesn't need to calculate the Hessian matrix directly. But then I'm going to introduce WhiteGrad, which is the optimizer that we developed, which is somewhere in between, right? So let me explain how it works. So if you think about the chain rule, so backpropagation is done using chain rule, right? So if you have a layer like this, if the input of the layer is called x, which is a vector, and the output of the layer is called y, right? Then the input is x, and the gradient of the output is round f over round y, where f is the loss function, right? Which is what we want to optimize. The chain rule says if you want to calculate the gradients of the weights, basically you can do this operation. You can calculate x transpose times round f over round y. That's basically the chain rule for calculating the gradients, right? So let me just explain. So x transpose is the activations of our examples in a batch. So if you have a batch of, let's say, 10 examples, x is 10 by 3, right? So each example has a gradient here, and so it's a 10 by 3 matrix. And then round f over round y is also 10 by 2, because for each parameter, or sorry, for each example, you can calculate the gradients. Right? The gradient of this representation with respect to the gradient of the loss function with respect to these parameters, right? So basically, we can. So this is the standard chain rule that is used in AutoGrad function. So this is the standard chain rule. And then the vanilla update rule, the most basic update rule is basically this. If you have the W's at the step T, what you do is you take a learning rate, which here we call gamma, and then subtract round f over round w using gamma. And round f over round w is exactly this, right? So we can rewrite the update rule as this. Wt plus 1 equals Wt minus gamma x transpose g, where g is the round f over round y, right? Okay, so let me repeat this. So if you have x, which is the gradient, which is the activations of this layer, and if you have g, which is the gradients of this layer, you just multiply x and g, and you basically subtract it from the gradients, right? So this is the standard. This is basically what happens in training. But then the idea is if you're able to whiten this, so this is a matrix, right? If you're able to whiten this matrix, we can get rid of the correlations, right? But basically that's what whitening does, right? Whitening gets rid of the correlations. So, but it is very difficult to whiten this. Why? Why is it difficult to whiten? the updates. I mean, why don't we generally whiten the updates? Because we know that if we whiten the updates, basically we can decorrelate the updates, right? So why don't we whiten? Well, we don't necessarily need Hessian, but it's still computationally expressed. Because like just the whitening matrix itself, if you have n parameters, the whitening matrix is n by n. So if you have a million parameters, still the whitening matrix becomes 10 to the 12 dimensional. Right? Yes, exactly. So we matrix, and using the covariance matrix, we can calculate the projection matrix. So the covariance matrix and the projection matrix are both interactable, or like practically interactable, right? So you cannot do you cannot whiten this. But then here is the key trick that we use. Even though you cannot whiten the whole thing, but you can whiten X and G. And whitening X and G is like computationally possible. And it's computationally tracked. Because X could be 1000 dimensional. Y could be again 1000 dimensional. The whitening matrix for a 1000 dimensional representation is 1000 by 1000, right? Which is easy to maintain and operate. I mean, easy to calculate, right? So the trick is, even though we cannot whiten the whole thing, we can whiten X and we can whiten G. Right? So if you're able to whiten X and G, we have shown that, of course, the whole thing is not whitened, right? But I mean, for all practical purposes, it will act like a whitened matrix, right? So, and it's easy to whiten X and G. I mean, it's not difficult because it's computationally possible. That's basically the key trick. So if the vanilla update rule that we discussed is this, like X transpose G, like times gamma subtracted from WT, what we do is we whiten X and we call the whitened X ZX, and we whiten G and we call the result ZG. And instead of multiplying X transpose G, we just multiply ZX transpose ZG. Right? So basically, we use the whitened version of X and we use the whitened version of G, and we multiply them. And that's how we basically change the update rule, right? But this is the key of the WhiteGrad optimism, right? So any questions?
Yeah. So at this moment, so this X is a matrix. One dimension is the number of signals in the linear layer, for example. And what's the other dimension?
So yes,
in the batch
X is yes. So X is B by M, where B is the batch size. B could be like 1000, for example. M is the dimensionality of the representation.
Okay. And the whitening happens for each batch separate.
Very good question. I'm going to discuss that in the next few slides, but essentially, we find the projection matrix once in a while, because finding the projection matrix is costly. But then we use the projection matrix at every batch.
And projection is D of this slide. Projection matrix, it's D before we perfect.
Sorry, what?
Projection matrix is which?
Oh, so I'm not showing the projection matrix here, but this matrix, I mean, but if you have X, the projection matrix is V sigma minus 1 V transpose. So this whole thing is the projection matrix, right? So if you calculate the projection matrix, you can store the projection matrix, and we can reuse it over and over in every. Yes.
Two issues I can think of.
Yes.
The dependence on the batch size, like batch norm, you need large batch size, small batch size. People use alternatives that don't work as well.
Yes.
And then if the covariance matrix is not full rank,
Yes.
you need some stability mechanism to make it inverted.
Yes. Very good
I-
points.
So do you need to multiply by the inverse or do you square root? So if you're whitening,
So, I mean, both points were fantastic, and I'm gonna address both. So, if you do a spectral decomposition, the spectral decomposition gives V sigma sigma squared V transpose, right? But then the projection, the ZCA whitening transform is defined as the following. You take your X and then calculate V sigma -1 and then V transpose.
there's the square root of the covariance. The inverse square root.
Yes, but then the thing is, sigma is a diagonal matrix.
Yeah, but you need to do the eigen decomposition.
Yes,
Not
you need to do eigen decomposition, exactly. You need to do eigen decomposition, but then as soon as you are able to do eigen decomposition, then you can like take the inverse of every, I mean, you can calculate 1 over each of the eigenvalues, right?
And do you do this on a per layer basis, or do you do
Yes,
it?
this is done on a per layer basis. But I mean, all questions were very good. And I'm going to discuss, I mean, the answer to both of your questions. Let me see if I have a slide here. Oh, okay. So the answer to the problem of having a small batch size, right? So you said if the batch size is too small, then the gradients, I mean, then it's not going to be full rank. So that the matrix that we want to calculate its eigenvalues, it's not going to be full rank, so it's going to have plenty of zero eigenvalues, right? But then we use a trick, and the trick is when we calculate the covariance matrix, we calculate an exponential moving average of the covariance matrix, right? So like, for example, if you have 1,000 batches, for example, in your training, all of the previous batches all contribute to the current covariance matrix, right? So like, for example, in Adam, we used to use an exponential moving average of the moments, right? Here we use exponential moving average of the covariance matrix. And every new batch that we see, we update the covariance matrix like this. So for example, X transpose X multiplied by beta, which is like very small, like, I mean, very close to 1, which is like, for example, 0.99, right? So it's like, it makes a very small contribution to the covariance matrix, and Sx is the covariance matrix, right? So this way, we won't have that singularity issue, right? And it doesn't depend on batch size, because you can make your batch size 10 times smaller, and you can make your beta, for example, instead of 0.99, you can make it 0.999, right? So effectively, I mean, it doesn't depend on batch size, right? So then the other question is, of course, whenever you do spectral decomposition, you get plenty of eigenvalues that are close to 0, right? You guys that worked on random matrices, I mean, should know this, right? You get plenty of eigenvalues that are close to 0. So what we do is we replace every eigenvalue that is close to 0, we can replace it with a very small epsilon number. And this is also quite similar to what Adam does. In fact, Adam adds this epsilon, right, in the denominator to avoid division by 0, right? So the way we use that is, we basically do the same thing. But for us, division by 0 is a much bigger threat, because when you calculate eigen decomposition, in practice, a lot of eigenvalues are close to 0, right? So basically, we need to do this epsilon trick to avoid division by 0. But both questions or both points were very good. So this is the algorithm. I mean, this may look complicated and tricky, but don't worry, I'm going to explain. So Sx and Sg is the exponential moving average of the covariance of X and G. If you recall, we had X, which is the representation of the input, which is the input representation, and we have G, which is the gradient of the output. So for every batch, we have X and G. So we use these two exponential moving averages to basically update Sx, which is the covariance of X, and Sg, which is the covariance of G. And then once in a while, just once in a while, we update the projection matrix. So for Sx, we use Px, which is the projection matrix, and we use Sg, which is, we use a PG, which is the projection matrix for the gradients of the output, right? So once in a while, we update Px and Pg, and then we calculate Zx, which is XPx, right? So basically, it means that if we have representation X, multiply them by Px or project them into a new space and call the result Zx. And we do the same thing for G. And instead of updating W with X transpose G, we update W with Zx transpose Zg, right? We use basically the white-hand version of X and the white-hand version of G to update the parameters. And then this is how we update the projection. If the input is S, then we do eigen decomposition, as you said. And then we get the eigenvectors and eigenvalues. And we calculate sigma epsilon minus 1, which basically makes sure that none of the eigenvalues are 0. And then it calculates V sigma minus 1 V transpose, which is the new projection matrix. So basically, this is the projection. There are a number of things that I didn't discuss here, but they're not very critical. One is, I didn't show how we do momentum, but you can think about how we do momentum. It's not typical. You can do bias adjustment, which is some trick that is used in other optimizers. I don't want to go into the details. It has a very small improvement effect. And then also the initialization of the covariance matrix I'm not showing here. Right? So basically, this is the way the optimizer works. And then if you think about it, this is the first optimizer that doesn't operate element-wise. All of the previous optimizers, they all used to operate element-wise. So like Adam processes each parameter completely independent as every other parameters. And basically all of these optimizers were element-wise, but this is not element-wise. So we use matrix multiplication stuff in the prediction, in the process. And then the results are also promising. So this is a deep model that uses convolutional neural networks on MNIST, like standard task that people use to compare optimizers. And this is the loss for the red curve is the loss for a stochastic gradient descent. The green curve is the loss for Adam, and our loss is the blue curve, which is like significantly, it drops significantly faster than Adam and stochastic gradient descent. And then not only the training loss goes down faster, but also the validation accuracy also increases faster. So, like this is again the validation accuracy on a stochastic gradient descent, using a stochastic gradient descent on Adam. And as you can see, our validation loss is significantly, validation accuracy is significantly higher. And not only it's higher, it's also more stable. And this is the result on a vision transformer on Cypher 10. And as you can see, the training loss goes down significantly faster, and the validation accuracy is also fast. Goes up faster. And this is the same thing for Cypher 100 and the training loss, which is again better, and the validation accuracy, which is again improved. So, I mean, the results are also promising.
You assume the hyperparameters you use are the same for SGD and your.
Very good question. The answer is here. The main hyperparameter is the learning rate. Of course, the optimum learning rate for Adam and stochastic gradient descent are different. So for Adam, usually the optimum learning rate is 0.0001, 10 to the minus 4. But for stochastic gradient descent, people use somewhere between 10 to the minus 1 and 10 to the minus 10. Sorry, it's 10 to the minus 1 and 10 to the minus 2. So something, I mean, it depends on a lot of factors, but this is the ballpark. So we optimize the hyperparameters for each of the models. And this is the training loss given the hyperparameter. Sorry, the learning rate. For Adam, the stochastic gradient descent and ours. And as you can see, after after a lot of epochs, the optimum learning rate for our technique is here. The optimum learning rate for stochastic gradient descent is here. The optimum learning rate for Adam is here. And this is a case where batch size is 10. This left column is in this left column, the batch size is 10. In the right column, the batch size is 6,000. So yes, so we optimize the learning, the learning rate. And there are
Solution, it seems it does not depend on batch size.
learning rate does not depend on batch size.
The optimal does not. If you compare the SGD for the two regimes, for the small and large batch size, it changes that. For yours, it's
Yes,
almost at the same point.
That's right. For our technique, it is less dependent on the size of the batch size. Yes, but the optimal points for SGD and Adam are different. Sorry. Oh, the algorithm. Yes. Yes. Good question. So when we calculate eigen decomposition, we use S. But this S is itself an exponential moving average of the that is calculated from all different batches. So like many batches participate in calculating the covariance. So basically the projection that is calculated depends on all of the previous batches. It uses the information from all of the previous batches. But it also gets updated over and over. Like for example, we update the covariance. I mean, we found that we can update the covariance matrix, the projection matrix once every 100 steps, once every 100 batches. I think you had a question, something here.
Okay, that's a question. The most of the patents
This.
It's just accurate, not there.
Oh yeah, why the accuracy is not very high?
Yeah.
Very good question. So these two columns are the result of vision transformer. These are not convolutional networks. And vision transformers are not designed for cipher. Right? That's the first reason. And then there's another reason, which is there are all sorts of bells and whistles. If you want to get SOTA, you should use all sorts of bells and whistles, right? You need to use augmentation, you will need to use learning rates, schedulers, you will need to maybe sometimes use like an auxiliary data set for training. There are a lot of tricks that people use to get SOTA. We don't do that. We just use the simplest form of this model. And in fact, you can you can try this. You can try this yourself. If you use vision transform on if you use vision transformer to do cipher 10 classification, that's what you get. That's the result. So we didn't use all of these bells and whistles, but we can. Of course, we can use. Yes.
false count of the x-axis is not the increase for the direction. And given that the unit
Fine.
yeah, it's much more in terms of coordination.
That's a very good question, right? So basically, you think, why are we using the same? I mean, why are we using epoch number rather than wall time?
Yeah, because if that works, for example,
Yes.
it will also be highly more
Yes.
convergent
Yes.
compared to other.
Again, very good question.
Not that.
Yes. So the answer here is the answer. The standard second order optimizers, they drastically increase the running time. And a lot of them are not even, I mean, you cannot even run them on vision transformer, for example, because in this vision transformer model, we have 63 linear layers. And each of them is around 500 by 500 dimension. So most second order optimizers, you cannot even fit them in the memory. The second thing is our overhead is actually quite small. So even in this case, the overhead of our technique is something like 10 to 20% only. And I can explain why the overhead is so low. You can look at the algorithm and try. I mean, I can try to explain to you why the overhead is so low. So look at what steps we do. For every batch, this batch needs to be loaded. Then you need to go through a forward pass, and then you need to go through a backward pass, and then you run the optimizer, right? So look at this. This is a 1,000. Let's imagine for a simple case where X is 1,000 dimensional. X 1,000 dimensional by 1,000 dimensional. So this is a 1,000 dimensional by 1,000 dimensional multiplication. This is a linear multiplication. And basically the whole thing is just a metric multiplication of order. If X is 1,000 by 1,000, so basically imagine N is 1,000, right? Then this takes ON cube computation. This also takes ON cube computation time. This is also ON cube computation time, and this is also ON cube computation, right? This update is again ON cube computation time, but it has a higher constant. So basically the entire thing is ON cube in terms of computational complexity. But then if you think about the forward pass and backward pass, they are also an ON cube, right? Because in the forward pass, you have a matrix X, which is the representation, like 1,000 dimensional representation for 1,000 examples. So it's like a 1,000 by 1,000 matrix, which is multiplied by a 1,000 by 1,000 matrix, which is the matrix of the linear layer. So in terms of computational complexity, the forward pass is ON cube, the backward pass is ON cube, and our technique is also ON cube. So we just increase the constant of ON cube, right? So basically, computationally speaking, we are also ON cube. But this is not the case for other second order optimizers, right? They all increase the computational complexity. And this is actually the key. And your question, I think, was quite important and relevant. That the key is, even though we can benefit from whitening and we can benefit from second order techniques, but we don't increase the computational complexity. So we just have a linear overhead. We just increase the constant. The most computationally expensive parts is this update, the eigen decomposition part, right? This is like the most computationally expensive step. But this we also don't do every step. We just do this once in a while, like once every 100 steps. So in fact, this is not even the bottleneck of the computation.
So code mode around 5 minutes left, and then now replying to the question.
Sorry, what?
Around 5 minutes left.
Yes, yes. Yeah, sure. So basically, I mean, another interesting thing that might be interesting to you. Let me show you this. There is a very interesting trick called sign stochastic gradient descent, where you take a gradients and take the sign of the gradients. You strip away the magnitude and only keep the sign, and update the model with the sign, right? This is like a trick that you can use. I mean, some people use this to avoid exploding gradients and vanishing gradients, but you don't necessarily need to do that. But then the value, I mean, the interesting part of sign SGD is the fact that it can tell you how good your signs are. So the sign of Adam and stochastic gradient descent are the same, right? They don't change the sign of the updates, right? But they're the same. And if you apply sign SGD on a stochastic gradient descent or Adam, here is what you get. So the red curve, the solid red curve is a stochastic gradient descent. The dashed red curve is the sign version. So basically, you only use the sign information to do the update. So you get this drop. For our case, the standard version is the solid thick blue curve. But then if you strip away the sign, if you only use the sign, you get the dashed blue line. And as you can see, even our sign stochastic gradients, or even the quality of our signs, are better than the quality of the signs of the updates that you get from stochastic gradient descent and Adam. So basically, this technique not only improves the magnitudes of the updates, but it also improves the sign of the updates. I mean, there are some other analysis that we can discuss. So yeah, just one last thing is, in GPUs, matrix multiplication is almost as fast as matrix addition, right? That's basically how GPUs work. Because matrix addition is memory bound. So matrix multiplication and matrix addition are almost the same. So basically, even though we introduced matrix multiplication in the optimizer, which is not the case in previous optimizers, but still we don't get much overhead. So that's it. I mean, there are a bunch of open problems that we can discuss, but I mean, if you have questions, I'm happy to take questions.
You have a paper?
Sorry?
Is there a paper on this?
So we haven't published the paper yet, but yes, we're going to publish the paper. Yes. 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 No, it's not. Yes, that's a very good question. I can give you a very maybe an interesting insight into why this is helpful for whitening. So here is the insight. Let's say you calculate X transpose G, right? Let's say one dimension of X is a representation, right? Let's say the dimension 1 of the representation is correlated with the dimension 2 of the representation, right? So if the dimension 1 and 2 are correlated, then if they get multiplied with something else, with some other dimension of G, the resulting values are also going to be correlated. So there are multiple reasons for correlation between two parameters in the update, in the multiplication. One reason that two parameters in the gradient updates can be correlated is basically the correlation of the constituents of X and constituents of X and G. So if there is a correlation in X, this is bad. If there is a correlation in G, this is bad. Of course, you're better off whitening X and G before you multiply. Of course, there are other reasons that may introduce more correlation. We cannot fix that, and we ignore that. But this is something we can fix in a good computational complexity. So that's what we do. Okay. So, yeah. I mean, there are a number of interesting open problems. I mean, I don't think we have much time, but later if we discuss with some of you guys, we can
May I ask a question about
Yes.
like the very early part, because you have very nice visualization with like it's correlated with the vector basically, right?
Yes.
But the question is, you need correlated on the one example, but for a batch, because they're all different sizes. They could be like one of them could be like very positive, another zero, another negative, especially like dropout. Like,
Good question. So basically, you're saying that it may be the case that there is a high correlation between two gradients per example, but when you come at the batch level, maybe some of the correlation basically fades away.
quantitative estimation.
No, we didn't do like a quantitative visualization to understand what's going on, but that's a very good question. So the thing is, if you have multiple random variables that are correlated, like like G1 and G2 are correlated, if you take a large number of them, like hundreds of them, and if you add them up, is this still going to be correlated or not, right? And I can give you an answer. You can rotate the axes. So right now, this is like one axis is G1, one axis is G2. If you rotate everything by 45 degrees, then you have this X, like G1 equals G2 axis, and then G1 equals minus G2 axis, right? So then if you think about adding up these vectors in that space, it's gonna, the effect is gonna be less. So you can, I mean, what happens is a lot of these gradients along this axis are gonna cancel out. And some of the gradients along this axis will also cancel out, but then the net effect of the gradients here in this axis will increase. But still, this process of finding or whitening is still helpful at the batch level too. Right. So I mean, if you can whiten at the example level, I mean, you can intuitively think that it will also be whitened at the batch level. Not exactly, but just to some degree. I mean, did I answer your question? Yeah. Okay, so thank you very much. Okay, it was nice being with you. Thank you very much.